All right, let's look at this question. Let's see what do we have. It's saying which of the following is the correct order of ionic radii? Okay, so it's given us a couple of ions, couple of orders. This is what we have to do. So this has taken us back to the chapter periodic properties. Let's see about that, right? So this is our periodic table. Obviously, we don't have all of the periods and all of the elements here. Obviously, as you can see clearly, we have scandium, we have yttrium, right? But lanthanum and F series, 4F, 5F, right? Lanthanum and then hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, all that. The entire 6th period, the entire 7th period, all of them are not here. Okay, cool. Apart from that, if we go back and take a look, right, we have titanium, we have titanium and we have manganese, which belong to, 3D series, not with the charge, without the charge, right? We have calcium, potassium, we have oxygen, fluorine, chlorine, potassium. So all of these are covered here. So yeah, this will do. Now, in general, we know that in a period, if we move from left to right, Z effective increases and so the radius decreases. Atomic size. Okay. We also know that if we go from top to bottom, since the shells get added, the size increases, right? Z effective, however, does not change or does not change much. Okay. Obviously, there are exceptional cases, but we know for most of them, we know the logic why. Okay. Now, this is the trend for, 3D series. We know that in 3D series, right, what happens is that although going from left to right, Z effective increases, but because of the shielding of the electron added, right, the effect increase in Z effective is countered, and you'll see that from chromium till, somewhere over here, not much change is happening in the radius, right? Okay. Apart from that, you'll see that, in towards the end, there is a slight increase because the repulsion counter because of the electrons, right, overpowers the increase in effective nuclear charge. But we don't have to go into that much detail for solving the case of Ti4 plus and Mn7 plus, right? Okay. Why is that? So let's go back. Let's have a look over here, right? So we have this over here, correct? What is the configuration for this thing? This pretty little thing, right? What do we have? The configuration is something like this. 3d2, 4s2, right? I'm writing them the configuration in the increasing order of principal quantum number. If I were to write it in the increasing order of energy, what would I do? I would write 4s2 3d2, right? So I'm just writing in the increasing order of principal quantum number. That is why I have 3d before and 4s later. Okay. Apart from that, what do I have over here? I have manganese. The configuration is Ar 3d5 4s2. Now, what is this option A doing? This option is saying what? Rip 4 electrons from titanium, rip 7 electrons from manganese. What? Yeah, rip 4 electrons, right? Rip away 4 electrons from titanium and rip away 7 electrons from manganese. What are we left with? We are left with 4s0 3d0, right? So first of all, entire 4th shell is removed. Electronic configuration wise, we are talking about argon. If you didn't know any better about what number of protons and neutrons are there inside, just looking at the configuration of the electrons, you would be like, oh, this is very similar to argon. That is what we have. Apart from that, there's one more thing, right? We have one, if you take a look over here, right? So both of these cases, Both of these cases, right, they share the electronic configuration of argon, right? So both of them have what? Both of them have 18 electrons. They are isoelectronic. But this titanium over here, this species, correct? This species has 22 protons, and this species over here, this species has 25 protons. Get the point what I'm trying to say, right? So obviously, if you have isoelectronic species, the one with the higher positive charge has a smaller radius, right? But even if you don't want to memorize that rule, you can clearly see that both of them have 18 electrons. One has 25 protons, so it will be pulling those 18 electrons quite compactly in a quite compact arrangement, quite strongly in a very compact arrangement. And the one with the 22 protons is going to also pull quite strongly, right? But the compactness of the arrangement is not going to be as much as Mn7 plus, right? So for that reason, what are we going to have? The actual order is going to be that the compactness of Mn7 plus is much more. So it is smaller in size as compared to Ti4 plus. Mn7 plus is going to be smaller in size than Ti4 plus. This order is not correct, right? The question asked for the correct order. If the question would have asked for incorrect order, I would be so happy right now. The first option itself, right? Nonetheless, let's proceed and let's see what other options are. So, what do we have? We have Ca2 plus, we have K plus. What is the scene? Same scene again, right? Calcium. What do we have? Atomic number. What is the atomic number? 20. Right? So 20 protons. Potassium 19, right? So basically 19 protons. Normally 20 electrons, normally 19 electrons. But now what do? You rip 2 electrons from calcium, right? So Ca2 plus, if you talk about, I would say it has 18 electrons. K plus, if you talk about, I would say it has 18 electrons. Proton wise, however, the story is slightly different, right? So electronic configuration wise, if you take a look, both of them have the configuration of argon, but one of them has a higher number of protons that will be smaller in size as compared to the other one. So Ca2 plus should be smaller in size as compared to K plus. All right. And with that, I am happy right now because I think I found my answer, option B. But just to be sure, let's go through other options as well. Okay. O2 minus. Okay. O2 minus. F minus. Electrons, protons. Okay. Cool. So I will be like 8 protons, 9 protons. That's pretty fine. Right? Okay. Now what do? We had 2 electrons, right? So 10 electrons and 10 electrons here as well because F minus 1 electron added. Now both of these have the electronic configuration of neon. The one with the higher number of protons is going to have a smaller size. So F minus should actually have a smaller size. And so this option is not correct because this is not the correct order of ionic radii. Okay, let's proceed to the next one and let's see what do we have. All right, cool. So when I look over here, right, I have Cl minus K plus. Now listen very carefully, right? What do we have? We have Cl minus, right? So what have you done? What have you done here, right? Cl, potassium, right? And you're like, sir, potassium is so large, right? Obviously, K plus is more than Cl minus. So potassium, look, sir, potassium here, so large, sir, look, chlorine here, so relatively small. But look, that large size is because of the fourth orbit. Fourth shell, rather, would be more correct. If we rip apart that extra electron, the outermost electron, it's back to being, electronic configuration wise belonging to the third shell. 4s1. We remove that 4s1. What do we get as the outermost subshell? 3p6. Right? So what do we have over here? Electrons and protons, and we have a Cl minus, we have a K plus. So Cl minus, Cl 17, 17 protons, K 19 protons. As a result, minus 1 added, so 18 electrons, plus 1, so 1 electron removed, so 18 electrons. So now again, we have the electronic configuration of argon, the one with the higher number of protons gets a smaller size. So actually K plus should be smaller in size as compared to Cl minus, and that is why this option is also incorrect. And with that, we have achieved what this question asked of us, and we have achieved that successfully, and we know that what we solved, that is option B, is indeed the correct response to this particular question. Alright, let's look at this question. Let's see what do we have. It's saying the formal charge on the phosphorus atom in PO4 3 minus ion is what? Okay, so let's just look at it. Okay, alright, so yeah, this is what we have. Now, isn't there some formula regarding formal charge? Right, that formal charge is equals to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2, right? I don't want to use this because then, this has other utilizations throughout chemistry as well. Bond energy, bond enthalpy, blah, blah, blah. We don't want to use B capital E. Okay. Now with that, let's see about that, right? So if I look at the right one, loose structure, I know this is a double bond. So there's going to be such a scenario. These are single bonds. So I can draw something like this over here, right? Okay. Now if I take a look, the valence electrons of phosphorus, that's basically what? 5. Okay. Then what do we have? Non-bonding electrons. It has no non-bonding electrons. Why? Because phosphorus there is an example in, PO4 3 minus is an example. I was going to say example of expansion of octet. I said, I think, example expansion. No, so I meant was that phosphorus in PO4 3 minus over there is an example of expansion of octet. Right? It's forming, it has 10 electrons overall in its valence shell right now, right? If you count the bonding ones as well, the shared ones as well. So, right, so it has crossed the octet, the 8 mark. It's utilizing all of its 5 valence electrons before the bonding 5 valence electrons. So it has 0 non-bonding electrons, right? Okay, and also, if you take a look, it has 10 bonding electrons in total. How so? Well, these, and these, right? These are 10 divided by 2, and that's basically what? Equal to 0, right? And this is essentially what we have. All right, cool. Well, with that, what is going to be the correct response? The formal charge on the phosphorus atom in this particular case is 0. All right, cool. With that, this question is concluded. This is what we have. All right, let's look at this question. Let's see what do we have. It's saying calculate the volume of 0.2 normal NaOH required for neutralizing the solution obtained by mixing 20 ml of 0.1 normal H2SO4 and 20 ml of 0.1 normal HCl. Okay, cool. Let's see what do we have. What are we going to do now? So, we have these volumes here. Let's proceed, right? So, we are talking about neutralization first of all. And as we can see, we have, 2 strong acids here, right? When I say strong acid, I mean that, if I say the general form as HA for a monobasic strong acid, I would say that it's going to completely dissociate into its ions, that is H plus and A minus, right? What I mean is that, if you take 2 moles of a strong acid like HCl, what you're going to get is, it's going to completely dissociate. You're going to get 2 moles of this thing and 2 moles of this thing, right? Complete dissociation. Complete breaking of HA into H plus and A minus. All right, cool. Also, we know that, it's much better from our understanding of normality and equivalence in mole concept. First chapter, if you remember, right? Nitika ma'am would have taught that. It's better to deal with equivalents, right? And since I don't want to deal with ugly numbers, I'm not converting this ml in liters. For that reason, we are now dealing with milliequivalents. Okay. So, milliequivalents, how do we get that? Volume in ml multiplied by normality, we get 2 milliequivalents. Okay. Volume in milliliters multiplied by normality, we get 2 milliequivalents. Voila, right? Or we also know that it's going to require 4 milliequivalents of NaOH or OH minus, correct? Which an NaOH, is also what? NaOH is also a strong electrolyte, right? So whether I say OH minus here or NaOH, in this particular case of NaOH, it's correct. Okay. Now the point is, we know the milliequivalents, right? We know the normality. What we have to find out is the volume. So how do we do that? Let's take a look, right? We have essentially what? 4 milliequivalents. So let me write it like this. Okay, cool. We have the normality as 0.2 and we have the volume here. Now this will be in liters because I converted this milliequivalents into equivalents. If I don't convert, if I let it be a milliequivalent, I'm going to get my answer directly in ml. And if I do that, my volume here comes out to be equals to what? 4 divided by 0.2, and that's 20 ml for me. And do we have 20 ml? Yes, indeed. And not just that, it is actually the correct response. B for Bangalore is indeed the correct response. And with that, we can conclude this question. All right, let's take a look at this question. Conjugate base of HCO3 minus is what? Oh, what are conjugate bases? Let's take a look, right? So I have an example in front of you. We can take a generalistic approach, right? Let's say we have HX. Okay. It gives you, H plus and X minus. Now, obviously, this is an acid. X minus obviously over here, right? So take a look at X minus and take a look at the backward direction, right? Take a look at the backward direction, right? So in the backward direction, this X minus combines with this H plus and forms HX. Now try to read it again backward, but from a different narration. Think of it like in the backward direction, X minus is consuming H plus. In the backward direction, X minus is consuming H plus, so it is behaving like a base, right? And it is basically in the solution as a result of dropping some HX into the solution, right? It has come from HX. And as a result, we can say that, it is a conjugate of HX and it is behaving as a base. Right? So it's a conjugate base of HX. X minus here is a conjugate base of HX. You can take another look, another example. We can have CH3COOH. We can remove one H plus from it. We can get CH3COO minus. Well, that becomes its conjugate base, right? Instead of writing minus H plus, we could have also written H plus over here, and that would have been correct as well. We would just have to, add the reversible sign over there, right? Okay. Now the point is, right, We can write this way, we can write it that way. It's either way, it's correct. Let's get back to the question. What do we have? Conjugate base of HCO3 minus. What are you going to do? You're going to remove an H plus. You're going to remove an H plus, right? So what do you do that? What happens when you do that? What do you get? You get CO3 2 minus, and with that, voila, we can indeed say that option D for Delhi, is indeed the correct response for this particular question. Alright, let's look at this question. Which of the following cannot act as Bronsted-Lowry base? Whoa. Let's look at that. What was base? Was it a proton donor? Was it a proton acceptor? Think about it. Which one here, right? Okay, cool. So, coming back over here, right? What do we have here? Which one is the Bronsted-Lowry base? Base only, right? Yeah, base. Which one of them is the Bronsted-Lowry base? Think about it. Which one? Right? NH3 here took H plus from HCl. Right? Look at those pinky whitish things over there with a lone pair dangling, right? When HCl, the green-white HCl entered, it grabbed the H plus, it grabbed the proton. It is a proton acceptor and hence a Bronsted-Lowry base, right? Okay, with that in mind, let's look at this question, right? So, OH minus can obviously form H2O, right? Why? Because you know what? We have this over here. We have something like this, correct? And if I have an H plus over here, we can easily form H2O out of them, right? I have SH minus. So I have something like this then again, right? If I have an H plus over here, we can easily form H2S. But if we have NH4 plus, right, we cannot form NH5 2 plus. Why? It is simply not possible. Via the rules of bonding that we studied in chemical bonding, by the rules of stability and octet, etc., we cannot have the formation of NH5 2 plus. There's simply not enough electrons to form this bond. There's simply not enough space to hold any more bond, right? Or any valency left to hold any more bonds. And so NH5 2 plus cannot form. So I would say that is indeed the one species that cannot act among the three here as a Bronsted-Lowry base. And with that, we know that we have solved it correctly. Option B for Bangalore is indeed the correct response for this particular question.